Alright, time for another draftphysics.com, debatephysics.com, also video presentation. So anyway, one of the trolls, yes, that I described in the previous video, is proposing an experiment where he's claimed to have already proven, and he will now prove again, okay, that springs don't collect momentum. So even though momentum is actually measured in newtons, which is a weight, and then originally was measured in foot-pounds, which is a weight, okay, momentum isn't collected by springs. Now, springs are used to make scales that measure weight. So you're stuck with a bit of logical non-continuity. How can a spring that measures weight not measure weight? I mean, how does it pretend that the Newton figure is some other newtons? So we're back to like the lever, or the pulley. You have a force of 9 pounds, you're overwhelming, and I can make the force out of anything. I can put anything on this other side of this lever. I could put a light mass over here, a heavy mass in here, and I can make 9 pounds of force, and somehow 9 pounds isn't 9 pounds. When, yeah, it is. You can't make 9 pounds into some other amount of pounds. And the same argument will go for springs. So the idea is basically, if you figure all this out, he's arguing that 20 newtons of force will compress a spring exactly the same as 100 newtons of force. That those two things hitting a spring will create exactly the same compression in the spring. They'll weigh the same. Even though they overtly don't weigh the same, even though they overtly have different Newton figure numbers, they somehow will weigh the same. So his experiment is he has, for some, I don't know, for whatever. He's made this complex device for, I would argue, little reason to do such a silly experiment. But anyway, so he's, instead of using a scale or something that's already been calibrated, he's just taking some spring and saying he's going to use a spring. And he's going to basically measure the difference, in sort of 1 gram increments all the way up to some numbers from 1 to 620 or something. Like somehow he could calibrate a spring with that many divisions, when of course he can't. So he has a huge differential between the objects when they hit the scale, their weight. Okay. And he's going to claim he's going to measure accurately these impulse measurements. So he's going to drop a heavy weight, a 25 times as heavy thing, okay, and a 1 time. So the one thing weighs 22 grams. This will weigh 600 and something or other. So we just consider it a 1 mass and a 25 mass. So he's going to drop the 25 mass 4 centimeters, which, by the way, triples its weight. 1 centimeter doubles, 4 centimeters quadruples. Yeah, so it's going to be 4 times its weight. Yeah, when it hits the spring. And the other one, again, is going to drop 100 centimeters, okay, 25 times the distance, as it turns out. And it's going to be in the gravity, say 5 times as long, to get 5 times the velocity. So that's the idea, is that it's moving at 5 times the velocity. So you have a 1 mass going 5 and a 25 mass going 1, and he's going to claim that produces the same compression in the spring, when again you can just calculate the momentum even without the weights themselves, just the momentum, and it tells you that well, no, there's a 5 times differential in the amount of newtons of force those two things will hit the spring with. So again, they insist on defending kinetic energy. So to protect kinetic energy from critique and criticism, they're going to propose that springs don't measure weight. When, of course, that's what they measure. They measure the newtons of force applied to the spring. And they, by Hooke's law, proportionally compress based on how many newtons of force you apply to them. So, we haven't seen the end result. I'm assuming it's all going to come down to what kind of little wacky little measuring device he's going to use, what kind of, filming he's going to do, and, but it's a junk experiment because he doesn't sit here and actually measure the compression. He actually puts the one mass on the spring and claims it doesn't weigh anything. So what's the point? It's kind of ridiculous to say the spring can't measure the one mass, and yet you're going to make this very precise measurement of the force applied when he didn't put a 5 mass on and then a 10 mass and then moving up to 25 and show that the spring can measure accurately, that the divisions actually can mean something, that 10 pounds does weigh twice as much as 5 pounds and that 20 pounds will weigh twice as much as 10 pounds, in this case grams. But anyway, so junk experiment that doesn't make any sense. Again, the force is measured in newtons. 20 newtons of force cannot compress a spring the same amount as 100 newtons of force. How is that possible? In what universe do springs not measure weight? And in what universe is weight not plainly momentum? Momentum's measured in weight. A newton is a weight. So I can't make any sense out of it. So but he's going to prove it. He's going to prove that he doesn't have to conserve momentum. All right. So that's all. Junk, garbage, trash. Not really worth my time. And so I'll move on to what I intended to do, which was a video on Feynman's interpretation of the concept of energy. Alright, so this won't obviously, I think, be a video for everybody, so it's going to be a little tedious. Feynman babbles on, makes jokes, wastes a lot of time, frankly, and not getting to the subject, and so there'll be some of that in this video. Sorry, I thought I had this all fixed. I gotta make sure the volume is tolerable. Yeah. All right. He first was talking about these are all conservation laws. So he first did charge, and then that ended up talking about all kinds of nonsense like quarks and whatnot. So that was turned to rubbish, and then he's now on the subject of energy conservation. So he just uses the word energy conservation, and from my perspective, it's just lying to sit there and pretend that energy is summed up as kinetic energy. Is that what you mean when you say the word energy, that everybody has to automatically put the word kinetic in front of it, and they can never think of energy as being momentum energy? So obviously for me, my entire life, I really didn't realize they actually did this 1/2 mv squared thing until, like, I don't know, 7 or 8 years ago. Hathaway brought it up, and it's like, what the fuck? He was sort of implying that it was a what the fuck equation, and I certainly said, oh yeah, they do say this kinetic energy thing, and you're just like. Because yes, my entire life, energy was momentum. What else do you need? You don't need to understand anything else. It's mass and velocity. Why would I square? Why would I think that because something is lighter and faster that it's got more energy? It still has to move stuff by giving it its momentum. It can't give it something else than momentum. Momentum's the only thing you can exchange, and that's what all the experiments are demonstrating. Especially all of the inelastic experiments are clearly demonstrating the only thing you can exchange is your momentum. You can't give anything other than your momentum. It's all you have. The pins are only going to get knocked down because the ball hits them and gives them the momentum the ball had. The ball stops, the pins move. That's how it works. Pool table. momentum all over the place. There's no kinetic energy anywhere. And we'd all know that if they, put different weight balls on the table, and then you'd realize that every time you're making an exchange between two things of unequal mass, the one theory tells you a story that's not going to be true. You're not going to be able to exchange your kinetic energy. You're only going to exchange momentum. All right, long preambles, but whatever. So, like I said, not a video for everybody. And such.
Another law which was for a while believed to be true was that the total mass of an object stays the same. It depends on how you define mass and whether you get mixed up with the energy nowadays, and I will disregard this mass law until we come to the conservation of energy. But the mass conservation law has been contained in the next one, which I'm going to discuss now, which is the law of conservation of energy.
So yes, it's fine. Look, I mean, presentations are all presentations, but it's a little bit funny. Yeah, I'll get around to it, like right now. Yeah.
The law of conservation of energy is the most difficult abstract one and the most useful, as a matter of fact, of all the conservation laws. Understand than the charge in these other ones, because in the charge in these other ones, it's obviously merely the mechanism is perfectly clear. It's a
okay. So I'm just saying that obviously energy is so simple if you just leave it at mv. If you just leave it as momentum, you always just rely on a momentum and always follow the momentum. We're back to the Descartesian perfection of just recognizing that energy just moves from object to object to object to object to object to object to object, and it's not any more complicated than that. So there is no, very unconfusing.
Conservation of the object, sort of. I mean, not quite, because of this problem that we get some new things from old things.
So I almost wanted to play that clip. So he's pointing about how neutrons are made out of protons and electrons. So again, just because people have argued against what I've stated when I've stated that a neutron is just a proton and an electron, very close together, it's the smallest dipole. And yes, it has a neutral charge overall. From a distance, it's going to look purple, but up close, it's going to look blue and red.
But it isn't. It's really a matter of counting. But the conservation of energy is a little more difficult.
So it's a matter of count. So for the conservation of charge, he's saying it's all a matter of counting how many charges there are. Now, I would obviously argue that energy is the same way. There is a quantum of energy that's built into the whole photon argument that Einstein made, and that it can be equally just counted. You can just count how much energy something has and how much it has to give. And the easiest way to count is just to take the mass and multiply it by the velocity, and it makes perfect sense.
Here we have a number which is not changed in time, but the number doesn't represent the number of any particular thing. I would like to make a kind of silly analogy to explain a little bit about it.
Right, so he's just going to make an analogy to conservation. And obviously, mv squared creates all kinds of problems in terms of conservation, because every time you convert energy from a fast thing to a slow thing, a heavy thing, a light thing to a heavy thing, you lose tremendous amounts of kinetic energy. And obviously the vice versa argument can be made. So this doesn't make any sense, and it's it's just unfortunate that he's saying the universe runs on this notion of energy when he's not even defining the energy as a specific kind of measurement. So he never writes down 1/2 mv squared, but that's what he's talking about.
And I want you to imagine that a mother has a very difficult child. Well, not necessarily difficult, but she has a child who she leaves alone in a room with 28 blocks.
So I've referenced this before. I think I probably played it before, but it might have been a while ago. So he's just basically going to say that, as scientists, you're going to play this role of detective, and you're going to try to figure out where the energy went. And so, I mean, the obvious places you could look are movement, vibrations, and then you could look for heat. Lots of ways to find the energy. I guess I should mention some troll, okay, posted a comment today, and I blocked him immediately because he started a comment with bro. Okay, so if you're going to write a comment and start it with saying bro, I'm just going to say fuck you back. Okay, I'm not your bro. Shove that shit. So don't bother. Don't bother commenting if you can't, in some reasonable way. I don't want introductions. I don't want you to say hi. I don't want any of that bullshit. But I certainly don't want to be called a bro or a dude. So if you can't do better than that, fuck you. All right, anyway, but he's making some stupid argument that somehow sound moving through something takes in a tremendous amount of energy or something, and it really doesn't. So if you really measure how much energy it is, it's a speaker kind of proves the point, right? I mean, speakers can make an awful lot of sound in a very small amount of energy applied.
The indestructible, absolutely indestructible blocks, like the charges. And the child plays with the blocks, and then during the day, and when the mother comes back, she discovers.
So he's basically saying that energy isn't in discrete chunks, and then he uses a block analogy that basically is saying that yes, the energy is discrete in the sense that you could compare it to blocks, and you could even say the blocks are made out of smaller blocks. But I mean, it's all add upable as a quantity of something.
Indeed, there are 28 blocks. She checks all the time the conservation of blocks. Well, this goes on for a few days until one day when she comes in, there are only 27 blocks. One block she finds later outside the window. He threw one out the window. So first we must appreciate the conservation laws involved, that you watch out that the stuff that you're trying to check doesn't go out.
Right, so he's saying the obvious thing, okay, is that you're losing energy to some radiant heat or sound or atmosphere moving or something else, so you have to always account for those things. And then you have to account for what's coming in, which is the problem for like an air track. You have to be aware of the fact that you are introducing energy into the system, and it might not be even or symmetrical or benign to the results of the experiment.
Some war. And the same thing could happen the other way if a boy came to play with him and brought in some blocks. Of course, those are obvious technical matters that you have to be careful of when you talk about a conservation law.
Right, so you don't let anything fly out the windows, and you don't bring anything in if possible. So you don't want to try to create your frictionless environment, okay, by introducing some other energy source,
But
if possible.
now suppose, however, that when the mother comes to count the blocks, she finds there are only 25 blocks, but suspects that in a little toy box, in a box that the boy has, he has hidden the blocks. So she says, I'm going to open the box. He says, no, you cannot open the box. How can she tell? She's a very clever mother, unlike most. She would say, the box weighs, I know when it's empty, 16 ounces, and each block weighs 3 ounces, so what I'm going to do is I'm going to weigh the box. So she would have another thing, number of blocks seen plus weight of box minus 16 ounces divided by 3 ounces.
Right, so it's just adding these factors that you'd have to account for, like air resistance or even humidity, all these little different variables that will be stealing some of the energy from the experiment. So in the case of the lever, okay, when you go to calculate your equalities, you got to recognize that you have to move the lever. This mechanism is going to make something move, and this mechanism is going to absorb some percentage of the energy depending on its mass. And so you have to figure that you don't have the same expectation. When you put 2 in over here, you're moving the lever, it's absorbed some of the energy, and you're not going to get quite the same amount out the other side because you've used some of it to move all of this matter.
And that adds always the same to 28. Goes on for a while until it doesn't check. What you notice is that the dirty water in the sink is changing its level. So we have the water level. Height of water in sink.
Yeah, I sort of think you could cut this a little shorter by not first writing it out. It's not that interesting. Just pointing out that there's always variables in an experiment, and you have to be aware of the variables.
Minus 6 inches, which it is when there's no block in it, divided by 1/4 inch, which is the height that the water rises when a block is in the dirty water. Now, as the boy becomes more ingenious and the mother...
So I think it would have been more interesting if he would have gotten to like a thermodynamic argument that all of this energy, okay, can be in big things, but in most experiments, the end product is going to be silence. That is, you're going to convert a bunch of linear motion into something else, and that's the part where you get into the more interesting subject of heat, and that heat is, in fact, you can't make heat without doing work. So heat is part of the energy of a system, in the sense that you could argue the linear motion is a form of heat that you can measure because it's all in one direction, and that eventually the energy is going to be dispersed in all directions, and it's not going to be as easy to measure. But I mean, I think if you're going to talk about energy, you really have to talk about it in terms of thermodynamics, since the energy goes from that cycle. That you can't get the energy into a big thing, okay, without heat.
That continues to be ingenious. More and more terms must be added on here, which all really represent blocks, but from a mathematical standpoint are abstract calculations, because the blocks are not seen. Now I would like to draw my analogy and tell you what is common to this and the conservation of energy and what is different. Suppose that you never saw the blocks at all, that in any one of the situations there were never any blocks. Then the mother would be always calculating a whole lot of terms, which is called blocks in the box, blocks in the water, blocks and so on. But there are other differences, that there aren't any blocks as far as...
So that's his assertion. So that I would obviously disagree that the way energy is transferred, it's obviously a something. So when something's moving, it's different than when it's not moving. It has something. All right, so that would be the argument. And that in the real universe, yes, we have to live with relativity in the sense that we can't see the whole picture, so we can't tell who's actually moving. But we can certainly make some reasonable deductions that, yeah, if I have water spinning in a bucket, I can figure out the whole universe isn't fooling me, okay, to create the illusion that the water's spinning in the bucket. So we know that certain things do have real motion relative to other things that don't have that motion, that it's additive motion, that whatever motion we have collectively, something else has some extra motion that we don't have collectively. All right.
We can tell. And that the numbers that come out here are not integers, unlike the case of the blocks with the child.
So he's saying they're not integers, but obviously I would say that, well, Einstein demonstrated pretty much that they are integers and that it's in clumps. So, you know, all the forces have to be understood to be something like light. It's all got to be. It's all moving the same speed. All the invisible forces have to be something like that. And if light is quantized, the rest of it might as well be.
Suppose, I mean, it could happen.
But clearly, in every example you can provide that's consistent with conservation of energy, the logic is obvious. Why is it conserved? Well, because you can't create it and you can't destroy it, because there's a certain amount of it. And why would you say the amount of it is this mystical, magical substance when it's just as easy to say, okay, it's in this form of force, And when something's moving, it's because it's interacted with more force going one way than the other way, and that's why it's going that way. It's because it has more force in that direction.
Happened to the poor lady that when she calculates this number, it comes out 6 1/8 blocks. And when she calculates this number, it comes out 7/8 of a block, and the rest of them give 21, still 28. That's the way it looks. So what we discover is...
Yeah, it really doesn't. So whatever. I mean, obviously the discrete bits are very tiny, so, you know, you can measure billions and trillions of them all the time, and so you're going to get non-integer answers merely because the decimal places aren't, you can't calculate all the decimal places.
That we have a scheme in which we can find a sequence of rules, and from the rules, each one of the different kinds of calculations we call calculating the same thing, number of blocks, or energy, by different rules. And then we...
So there's no different rules. Like I said, so if you just follow the momentum, there you don't need any different rule. You're just saying what's moving. And obviously heat is movement. So, and we can measure the heat with a thermometer. So, I mean, you know, we can quantize the movement. We can see it. We can detect it with instruments. So, you know, I don't see this as an issue, frankly. That somehow we have to believe the energy is amorphous and, you know, not physical.
Add all the numbers together from all the different forms of energy, it always adds up to the same total.
So that's the end result, right? So if it's the same total, then why you're playing a game that it matters whether you call it discrete or you call it magical. You're going to measure it as a quantity that can't be changed.
But as far as we know, there are no real units. It's not made out of little ball bearings.
So says him. So I would argue it's obviously made out of little ball bearings. Yes, little bits moving the speed of light. And they hit electrons and protons, and that's the real universe. There's no other universe. That's the one that where everything really happens. Everything else, we're pretending it happens because a whole bunch of that stuff is doing stuff, but nothing originates in this universe. This is byproduct universe. The universe where the action actually happens is where the electrons and protons live.
So it's abstract. It's purely mathematical. There
Nah, bullshit.
exists a number such that you can calculate and it doesn't change.
Well, it doesn't matter, right? I mean, this is like a religious question they've implied or put into physics. They don't have any real balls to, I mean, evidence balls to make these assertions. They're just telling you that's their opinion, okay, that it doesn't have a reality. And, but there's no reason to believe that opinion.
Cannot interpret any better than that. And this energy...
The end result is we agree that it has to be conserved, that you can't create it and you can't destroy it.
He has all kinds of forms, analogous to the blocks in the box and blocks in the sink water and so on.
Right, so and I would argue all the forms are all the same form. It's just electrons and protons in the end moving. They're the part that creates action in the universe, and without those things moving, the force is irrelevant. So, the force can't act on the force. The force can only act on electrons and protons.
There is energy due to motion. It's called kinetic energy. There's energy due to gravitational...
So it doesn't mean anything, right? I mean, obviously the energy due to gravitational is the same kinetic energy or momentum. So what's the point? So instead of saying, look, we have this energy duality, we like to sometimes call it kinetic energy, and then we sometimes like to call it momentum. He doesn't really deal with the energy duality at all here. And again, to call gravitational energy something other than it's either kinetic or momentum. I mean, you can't categorize it as anything other than that. That's what it is. It's masses moving velocities. That's what gravity causes, a mass to move a velocity. How is that not either kinetic energy or momentum? It's not gravitational. It's the same motion. It's the same action. There's no difference between gravity giving something momentum and a football player giving something momentum. What's the difference? the thing will end up it'll end up being a mass moving a velocity. It doesn't matter how it acquired being a mass moving a velocity. It only matters that it is a mass moving a velocity.
Interaction, the gravitational potential energy it's called. There's a thing called thermal energy.
So we know thermal energy is just heat. That's just the vibration. So you've added more movement to the electrons and protons and the atoms themselves, and that energy is also momentum.
Electrical energy, light energy.
Right, all the same thing. Light energy would be a force, so you'd put that into the category of being more elemental, but as Newton stated, the force is proportional to momentum. So you measure the force, you're just measuring a quantity of motion, a quantity of momentum. And such. Alright, continuing.
Elastic energy and springs and so on. Chemical energy.
So we know elastic energy. What's the point of saying something like that? We know the spring is also just creating some sort of mass moving a velocity. So no point in calling it elastic energy like it's some kind of different kind of energy. It's not any different.
Clear energy, and there is also an energy that a particle has from its mere existence. An energy that depends on its mass directly.
So that would argue that's rubbish, okay? Nothing... an electron not moving doesn't have any energy. But the fact is it takes up space. And space does have energy. It does have pressure. So as soon as you introduce matter into space full of pressure, you displace the pressure. That is, you make the vessel smaller. So if I have a vessel that's full of a compressed gas and I put a steel ball inside of it, I've just increased the pressure of the compressed gas because I've taken away some of the size of the vessel. I've changed the volume the gas is in. So that's the only energy mass has, is its displacement energy. Its size is displacing space in the universe. By displacing space in the universe, you are compressing the force and giving it more pressure.
The contribution of Einstein, as you undoubtedly know. E equals mc squared is what I was talking about, which is a famous equation.
Yeah, so it really has nothing to do with anything, and the fact that you get energy out of atoms when you break them is because you're breaking a condition that exists of charge. So you're taking a bunch of electrically charged mechanisms and you're breaking the cohesion between them, the symmetry or balance between them, and they react aggressively when you change their circumstance. So if you have a proton, an electron, and a proton, and you knock the electron out, you can imagine now the two protons see each other and react violently.
Mystic law. Now, actually, although I mentioned a large number of energies, I would like to explain that we're not completely ignorant about the thing and that we understand the relationship of some of them.
Right, so now he's going to basically, this is what he should say, is that, frankly, because he believes it, it's all the same thing, okay? So there's just no point in calling these things different forms or different words because they all just have to do with mass and motion. Even if you believe in 1/2 mv squared, you have to concede mv is in the core of it. It's masses moving velocities. That's all there is.
For example, what we call thermal energy is to a large extent merely the energy, the kinetic energy of motion of the particle.
So he called it the kinetic energy when, yes, he could just have easily said the momentum of particles moving, right? No rule against that. It's just their choice to keep emphasizing the existence of this fable.
Inside an object. What we call elastic energy and chemical energy both have about the same origin, namely the forces between the atoms. When the atoms rearrange in a new pattern, some energy is changed. That quantity changes. That means that some other quantity has to change. So, for instance, if the chemical energy changes, then heat energy is changed. So that in a burning something, the chemical energy changes and you find heat.
Right, so the energy is just in the positions of electrons and protons, and as you change their position, you bring them closer together and further apart. Obviously, you create expansion. The size of something changes. Its profile in the universe changes, and you end up with pressure changes based on those changes. So obviously, when you mix hydrogen and oxygen and you create big water molecules, you're basically displacing, space and creating an increase in pressure.
You didn't have the heat before, because it all has to add up right. And but elastic energy and chemical energy are both interactions of atoms, and we now understand the interactions of the energies of the atoms, or those chemical interactions, or those interactions of the atoms, to be a combination of two things. One is electrical energy, and the other is kinetic energy.
So kinetic is the bullshit part, and really it's about, charge. It ends up being magnetism. So you're basically just saying in a lot of circumstances you're just taking a bunch of polar atoms and changing their position, which is basically sliding magnets across each other, and there's places the magnets want to be and you're moving to places they don't want to be.
Again, only the formula for it is quantum mechanical instead of the usual. It's a little different.
Yeah, drivel dravel.
Light energy is nothing but electrical energy, because light has now been interpreted.
So, again, they've now interpreted it. Yes, that's their business, but clearly it's not what they claim it to be, Light is, as Einstein described it, discrete bits of energy quanta.
But it is an electric and magnetic wave. The nuclear energy has is not represented in the terms of the others, but as a result of what do we say? Due to nuclear forces. Well, we didn't say anything.
Right, you didn't say anything, but you can't say anything because you have just invented a force, the strong force, and you just pretend the source of the energy is the strong force, that you don't know where it came from or how it manifests or where anything about it. It's just a magical force they claim to exist that pushes protons together. And again, my simple argument is if you stick an electron between two protons, you are going to bring the protons really close together. No problem. You don't need any strong force.
But nuclear energy is not connected yet to the others. I'm not just talking about the energy released. In the uranium nucleus, there's a certain amount of energy, and then when this thing disintegrates, it changes the amount of energy in the nucleus, but the total amount of energy in the world doesn't change, so a lot of heat and stuff is generated in the process in order to balance that.
Yeah, you break a big nucleus into two smaller nucleuses. Yeah. And you have leftover bits that are going to fly away very fast.
Thing out. Now this conservation law is very useful in many technical ways, and I wish I could give you a number of them.
So there's no technical way if you don't make this clear distinction. You have to figure out one way or the other. Is energy momentum or is energy 1/2 mv squared? Obviously I've been arguing aggressively that there's no good evidence of 1/2 mv squared, and there's a ton of good evidence that momentum won't steer you wrong. Lots of physicists say, nature can't finagle momentum.
I'll give you some very simple ones to show you how, from the conservation of energy, and knowing the formulas for the energy, which are not those, you can calculate, you can see what some certain things have to happen. In other words, many laws are not independent laws, but are just secret ways of talking about the conservation of energy.
So he's going to get to a lever now, and basically describe how it conserves momentum. So it's all this kinetic energy talk. Energy means kinetic energy, and yet he's going to use a momentum argument to talk about conservation. And clearly if you use his analogy, his drawing, and you calculate the kinetic energy, you didn't conserve the kinetic energy. You conserved the momentum, not the kinetic energy. So that's the joke. He's talking about a conservation law. He's going to use an example where he doesn't conserve it.
Or better, knowing the conservation of energy, you can understand a lot of laws. The simplest one is the lever if this is a lever on a pivot, and let's say this distance is 1 and this distance is 4 times 1 foot and 4 feet, then first I must give you the law for gravity energy. And the law for gravity energy is to take, if you have a lot of weight, you take the weight of each weight.
So obviously you can do the lever horizontally, so no problem. Horizontal lever, no problem. So you don't have to use gravity as part of the equation. And frankly, if you really think about it, gravity doesn't have much to do with it. In terms of the real thing that's going to create an oscillator, okay, in the case of the oscillation, is the fact that the lever itself, its mass, switches sides. Okay. Come on. I don't need this sub menu. Okay, it's broken. Yeah, I don't know what to do. Oh, there.
And multiply it by the height above the ground, and add this together for all the weights, and that gives all the gravity energy. Now let's put the ground right here. Now, the problem is this. Suppose that I have a 1 pound weight here, just to make it, or say to make it more complicated, 2 pound weight here.
Yeah, it'd be nice if we just left it as simple, but whatever.
And I have an unknown mystic weight on the other side. X is always the unknown. So let's call it W to make it look more, that we've advanced above the usual. Now, the question is, how much must W be so that it just bounces and it swings quietly back and forth without any...
Right, so you've balanced the momentums, right? But you won't be balancing the kinetic energy. So that's the joke of this analogy, is he's going to calculate W by just doing the law of the lever, saying it's 4 units of distance, 2 pounds, 8 is the answer. Now, if I put those values in, I'm not going to have the same amount of energy on both sides. I'm going to have 4 times the energy on one side by kinetic energy theory. So there is no conservation. So it's just sort of a, just demonstrating they don't take this at all seriously. They just switch gears anytime they want. They just decide one day I'm going to talk about momentum, I'll talk about kinetic energy, I'll use whatever formula I want for the particular circumstance, and it's all just bullshit.
Trouble. That means that the energy, if it swings quietly back and forth without any trouble, when it's set...
So it's not going to swing quietly back and forth unless you're balancing it, okay, by having the fulcrum above the masses.
This way. And when it's tilted up a little bit, say, for instance, if this has gone up 1 inch, the energy is the same. If it is the same, then it doesn't care much which way, and it doesn't fall over.
If you drill the hole right for the center of the fulcrum, then you can put the masses anywhere and they won't oscillate. They'll just say, okay, fine, I don't care. They're still balancing. They still have the same pressure they're putting on, but they're not going to move because the lever itself isn't switched mass. It hasn't taken mass and put it on one side, taken a little bit of mass, put it on the other side. And the case from below, you're doing exactly the opposite of the case hanging above. So when you're hanging above, you're putting more mass on the side that's higher. And in the case where you have the fulcrum in below, you're putting more mass on the side, okay, that is lower. So you're making the heavy side heavier. Yeah. So that's why it's very difficult to find the balance with a fulcrum below, and it's really easy to find balance with a fulcrum above.
A long time, this being 1 inch and that being 4 feet, you can figure out by proportion that this being 1 foot, this is 1/4 of an inch. So that the rule says this, that before anything happened, all the heights were 0, so the total energy is 0. After the thing is happened...
So we know the heights aren't proportional to the actual velocities, right? So we know that quadratic relationship exists, and so the actual velocities are going to be the square root of the height. So the actual momentum is going to be. So again, just more fake stuff. He's not going to balance the kinetic energies. The kinetic energies aren't balanced. The momentums are balanced.
We multiply the weights, unknown, by the height minus 1/4 of an inch. Add the other weight, 2, by the...
So that's all just momentum. So he talked about the height and the point, but he's obviously not doing what he's supposed to do, which is convert it into kinetic energy. He's just going to measure the momentum.
Height, 1 inch, and this should add up to the same energy as before. So that a quarter of W taken away from 2 is 0, and W must be 8. So that's how we find the laws. I mean, that's one way we can understand the easy law that you know, of course, the law of the lever. But it's
right, so he's saying there's a law of the lever, which is really just obviously, it has everything to do with quantity of motion, what was considered to be momentum by Newton's time. So there's really no, there's no law of the lever that applies to kinetic energy. They never modified the law of the lever to make it consistent with kinetic energy. There's no kinetic energy version of the law of the lever.
Interesting that not only this one, but hundreds of others of the physical laws can all be closely related to the various forms of energy. So I illustrate that only to illustrate how useful it is.
Right, so he just provided an example of momentum, conserving momentum, and he's making an argument that somehow kinetic energy was conserved when it wasn't.
Only trouble is, of course, it doesn't really work.
He likes doing that. It doesn't really work, but it's the only thing he's going to say is a very technical, small, irrelevant point.
I mean, if you did that, it wouldn't swing like this on account of friction in the fulcrum.
So, okay, see, so there's no friction in the fulcrum, so that's nonsense. It wouldn't swing because it does a little bit. I mean, if you try it, but it depends on how precise your fulcrum is. So if I put this thing on my finger, I balance it on my finger, well, then it's going to roll on my finger. So that will allow it to balance. See, it can wobble because it's on my finger. It's not on the string now. The string's not holding it. I'm holding it. So it will balance because it's rolling across a huge fulcrum. But if I make the fulcrum very precise and very small, then I'm really going to have a hard time finding the balance, because any little tiny bit I'm off, it's going to just swing down. So, I mean, these are little details, but all these details matter. And the physics audience, the science audience, despises details.
If I had something moving, for instance, it has kinetic energy like a rolling ball, and it's on a constant height, and it rolls along, and then it stops.
Right. So, again, kinetic energy. So we know, rolling ball is such an easy one to think of in terms of its momentum. I mean, it's a mass moving a velocity, a linear velocity. And then it has the complication of the angular momentum.
That's on account of friction. But what happened to the energy of the ball? And the answer is that the energy of the ball...
So this is clearly an argument being made that, yes, all you're doing is taking the momentum in the ball and you're converting it, exchanging it with the ground. So now the ground is moving instead of the ball moving. It's that simple. The ball loses its energy to the ground that can absorb it. The ground has lots of capacity to absorb motion, and so it's almost hungry for it and says, go ahead, move me, move me, move me. I'm made of lots of little pieces. My little pieces move really easy, so go ahead, hit me, and I'll take your energy.
Has gone into the energy of the jiggling of the atoms in the floor and in the ball. The world that we see on a large scale looks so nice when we polish a nice round ball and so on. It's really quite complicated when you look at it in a little scale. Little billions of tiny atoms with all kinds of irregular shapes are looked at in detail. It's like a very rough ball.
Yeah, so it's like a bunch of little tiny bowling pins, and every time we migrate across that surface, we're knocking the pins down. We're losing our energy to the interaction. So anytime you touch another material object, you're comparing your motions and exchanging your condition.
Boulder, really, when looked at finely enough, because it's made out of these little balls, and the floor is the same way, as a bumpy business made out of balls. And you roll this monster thing over the other, you can see that the little atoms are going to go snap, jiggle, and after the thing has rolled across, the ones that are left behind are still shaking a little bit from the pushing and snapping that they went through. So there is left in the floor a jiggling motion or thermal energy. And
there's a mass and a velocity in the floor. The truth is you just lost your momentum. And all the floor has, if you add up every single atom that's now moving more than it was before, every single bit of that will add up, just as the pin's motion and all of their velocities and then their impacts with walls and the heat exchange and all that stuff. If you add it all up, it's going to be the same amount of mass moving a velocity. The MV will be conserved. It's just now in the form of very small things moving.
Although at first it looks like the law of conservation is false, energy has a tendency to hide from us, and we need thermometers and other instruments to make sure that it's still there.
Right, and they haven't done any of that. So I haven't found one single ballistic pendulum experiment online where they actually measure the catcher. Okay, a lot of them are mechanical catching devices, so you can't really measure temperature very easy. But all the ones that have anything to do with a gel or clay or some other mechanism, they never measure the heat. They just claim it's there.
The first demonstration of the conservation of energy, the energy is conserved no matter how complex the process or no matter what, even when we don't know the detailed laws. The first demonstration...
So we know, again, there's no point in saying the energy is conserved if that doesn't include momentum as a viable candidate for conservation. But you can't conserve both. So again, the math doesn't work. There's no possible way to have energy exchange between different masses and have any capacity to conserve kinetic energy. It won't be conserved. It's just an absolute fact.
Of the law of conservation of energy, in fact, was not by a physicist, but by a doctor, a medical man.
So he's going way back. So I think this is the experiment done by the guy who was guillotined in the French Revolution because he unfortunately had the job of being a tax collector as well as being a scientist, and it didn't go well for him. But he's, and who knows what kind of torture he put the poor animals through. But he basically put animals in sealed vessels and then measured exactly how much food and air they were given. And then after they were done dying, he, found out how much energy was in the system, so to speak.
He demonstrated with rats that the total energy of the food put in before and the heat generated by you burn food and you find out how much heat is generated, and then you feed the rats the food, and it's converted an oxygen and it's converted to carbon dioxide the same way as in burning, and measure the energy in that case, and you find out that living creatures do exactly the same thing as non-living creatures. That the law of conservation of energy is exactly as true for life as not. As a matter of fact, it was discovered by this. Incidentally, it's interesting that every overall principle that we know that we can test on the great phenomena of life.
So we know they don't test anything.
Work just as well as for dead things. That is, there is no evidence yet that what goes on in living creatures is necessarily different. Or maybe more complicated, but that is necessarily different.
Yes, we're just machines. That's right. You're just animated matter.
Different than what goes on in non-living things. I mean, in the physical, as far as the physical laws are concerned. Incidentally, this amount of energy that's in the food, it'll tell you how much heat and mechanical work and everything that's generated is what you read. When you read up here about calories, you're not eating something called calories, but you're eating that measure of the amount of heat energy that's in the food. For people...
So, yes, it all comes down to, again, you could just argue you're eating momentum. You're eating a fundamental capacity to produce motion. So you're eating molecules that have stored in them something that can cause other atoms to move.
Who like to... Physicists always feel so superior and smart and so on that people would just like to get them once on something. And so I'll give you something to get them on. They should be utterly ashamed of themselves.
Yes. And, so now he's just going to bring up how, yes, why bother with all this crap of calling something a joule and a Newton and then saying they're completely different when they're exactly the same thing, really. They're just, all of them can be converted into each other. So there's no point in talking about horsepower and watts and joules and newtons and calories and thermal units or any of that crap, because it's all the same thing, and including weight. So if you're going to talk about a force and weight and momentum and pressure, they're all the same word. It's all the same thing.
Because they take the same thing, energy, and they measure it in a host of different ways with different names. Absolutely absurd. Energy can be measured in calories, in ergs, in electron volts, in foot-pounds, in BTU, in horsepower hours, in kilowatt hours. All exactly the same thing. It's like having money, you know, in dollars and in pounds and so on. But
so I wish he did an analogy that it's just money, you know, because that's all it is. It's just a currency. Energy is a currency, and all you can do is give it away or collect it. That's it. You can't destroy the nickels and dimes and dollars. All you can do is exchange them.
Unlike the economic situation where the ratio can change, these dopey things are an absolutely guaranteed proportion. If anything could be analogous to it at all, the only hope would be to say that there are 20 shillings to a pound, and that you have shillings and pounds, with one complication that the physicist allows, in that instead of saying he has 20 shillings to a pound, he says he has.
So this goes to all their units. You know, you could argue that they could get rid of the gravitational constant if they made the gravitational constant 1, okay, a unit of 1, and then just changed kilograms and meters per second to validate that 1, you know, to that argument. And then we'd have a meter would be a different length, like 17 inches or something. And then you don't need the gravitational constant.
Irrational rate.
So theoretically, you could argue the gravitational constant is only there because we haven't chosen the universe's preferable units. So if we use the units that are preferable to how the universe works, we wouldn't need the gravitational constant.
Ratios like 1.6183178 shillings to a pound. So, in addition to that, you'd think that the more modern, high-class theoretical physicists would at least use a common unit, but you can find papers with degrees Kelvin for measuring energy, megacycles, inverse Fermis is the latest invention. We don't need any more inventions. We should all measure the energy in exactly the same. We should measure the energy in 1 unit and let it be done instead of having all these different names. And it just shows that people are often also, they want to say, see, I should bring my little boy to show on the screen so that the audience will understand that I'm human. Well, the proof that physicists are human is the idiocy of all the different units which they use in measuring energy.
So it's kind of a shot at his own family. Oh yes, it's just a stupid nuisance creating families, and you know, it's just as dumb as having you know, too many units saying the same thing. So anyway, at least it's a, you know, the fact is, so there's a few moments in Feynman's lectures where he says something like when he says, I wish they wouldn't teach people that photons are waves because they're clumps and the thing don't work that way. And this basically stating pretty much that, yes, all energy is the same. And it's always going to come down to electrons and protons moving. And you might as well just have a name for moving an electron a certain distance, a certain velocity, and use that as the unit. So, sort of validates my point, is my point. Yeah, I think we should be finishing up here.
Now, we have a number of interesting phenomena in nature which present us some curious problems with energy. Has recently been discovered things called quasars, which are very far away and they emit a lot of light. They're enormously far away, emit a lot of light and a lot of radio waves, and have radiating so much energy that the question is, where does it come from? That is, after it's radiated this enormous...
So I don't know if this is an issue anymore. I guess quasars are really just galaxies that are really far away and big. Small in profile, but big in brightness. And I don't think that's an issue anymore with Hubble and the other stuff, but who knows?
Amount of energy, the condition must be different than it was before if the conservation of energy is right. Question, is the thing collapsed gravitationally? Is it different condition gravitationally? Is it coming from gravity energy, this big emission? Or is it coming from nuclear energy and so on? And nobody knows. Will you like to propose that maybe the law of conservation of energy is not right? Well, when a thing is investigated as poorly, I don't mean as incompletely as is the quasars, because they can't see so easy at such a large distance, it very rarely is, when a thing looks difficult, that the fundamental laws are wrong. It's usually that the details are unknown. Another interesting example of the use of the conservation of energy is in this reaction. It was first thought that neutrons turn to protons plus electrons. But the energy of a neutron is fixed, and that of a proton could be measured. And
so the energy of a neutron isn't fixed. Obviously, neutrons are critical. There's fast-moving neutrons and slow-moving neutrons, and the whole reason why they have to use uranium is because the neutrons are slow-moving neutrons and blah, 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 blah. So, I mean, it's a little bit ridiculous to talk about the standing or non-moving energy of a neutron, in my opinion. That's really no point. But anyway, won't get into all that. Let's jump ahead a little bit.
Constant, and so when it was discovered that that was false, everybody say it was a terrible thing that physicists found out they were wrong.
No.
It's about the regions that we haven't seen, or is no use to say that it's true in a region where you don't look yet, when you haven't looked yet. If you will not say that it's true in a region that you haven't looked yet, you don't know anything. If the only laws that you find are those which you just finished observing, then you can't make any predictions, and the only utility of the science is to go on and to try to take guesses. You see, the most likely thing is that the energy is conserved in other places. So what we do always is to stick your neck out.
Right, and but you don't ever fix the neck out part by actually someday actually proving any of it. So you just end up with a fable for 350 years, but you never bothered to test it. So again, they still think that light is twice as bent by gravity, but they really haven't tested it.
People like this, and that of course means that the science is uncertain. The moment that you make a proposition that about a region of experience that you haven't directly seen, then you must be uncertain. But we always must make statements about the regions that we haven't seen, or is no use in the whole business. For instance,
so again, it just ends up with them making antimatter and all kinds of silly nonsense. So it's really dangerous to just speculate without any obligation to ever show hard evidence.
In early experiment, the mass of an object changes when it moves because of the conservation of energy. The energy associated with the motion appears as an extra mass because of the relation of mass and energy. So things get heavy.
So that doesn't happen, right? So that's just Einstein's mush. So it's another guess at what happens when things are moving almost the speed of light, which
heavier when they move.
No evidence that they even can do that. That atoms can survive moving the speed of light.
It was first believed by Newton that this wasn't the case, that the masses stayed constant. And so when it was discovered that that was false, everybody say it was a terrible thing that physicists found out they were wrong. Why did they think they were right? The effect is very small, only when you get near the speed of light.
So again, the effect isn't demonstrated by evidence. It's just demonstrated by a theory that you all said was okay, and that's it. There's no proof of it.
Make any difference. If you spin a top, it weighs the same as if you don't spin it within very, very fine fraction. So you could say, oh, they should have said, if you do not move any faster than so-and-so, then the mass doesn't change. That would then be certain. No. The experiment happens to be done only with tops made out of wood, copper, steel, and so on. So we should have said that tops made out of copper, steel, wood, and so on, when not moving any faster. You see, there are we do not know all the conditions
yes,
that we need.
The problem is you can't measure it, so what's the point? Doesn't matter what it's made out of, you can't measure the effect because it's such a small effect.
For an experiment, it is not known whether a radioactive top would have a mass that's certain, but we have to take a guess. So in order to have any utility at all to the science, In order not simply to describe an experiment that's just been done, we have to propose laws beyond their range, and there's nothing wrong with that. That's the success. That's the point. And that makes the science uncertain. If you thought before that...
So, whatever. So we know that in the last 100 years, all they've done is make up all kinds of silly stories about all kinds of hobgoblins that live inside of atoms. A bunch of 400 piles of nonsense.
Science was certain. Well, that's just an error on your part. Now there are other... So we have here the energy, which we could put in our list. And it's conserved perfectly, as far as we know. But it does not come in units.
So it's just silly. It's not conserved. Kinetic energy is not conserved in all kinds of experiments. It's not conserved.
And now the question is it the source of a field? And the answer is yes. Einstein understood gravitation as being generated by energy. Energy and mass are equivalent, and Newton's interpretation...
So silly. Energy and mass are not equivalent, so no point in even saying it. It's silly.
That the mass is what produced the gravity has been modified to being the energy that produces the gravity. There are other laws that are similar to the conservation of energy in the sense that they're numbers. I haven't very much time to describe them, but I'll mention what they are. One of them is the momentum. It means if you take all the masses in an object and multiply them by the velocities, for instance, and add it together, that's the momentum of the particles in it anyway. And that total amount of momentum is conserved.
So they can't be. So it's just wrong to say it. It can't happen. You can't conserve both. Anytime you transfer energy from things of different mass, those two numbers no longer have any proportional relationship. They can't both be conserved.
The energy and the momentum.
If this lever shoots a one mass object at 1.4 the velocity, or 2 velocities, that's a huge difference, okay? It's not the same thing anymore. You can't say you conserved it because you didn't. Because one means you conserve the momentum if one outcome happens, and if the other outcome happens, you conserve the kinetic energy. But if the momentum is conserved, the kinetic energy is destroyed, and if the kinetic energy is conserved, then the momentum is destroyed. Just a fact.
Now understood to be very closely related, and so I should be in the same column.
So what's up closely related? It's again, mv squared is closely related to mv. Oh, no, it isn't.
In this conservation law. Another example of a conserved quantity is angular momentum, an item which we discussed some time before. The angular momentum is the...
So this is all sort of a dodge. I don't know if there's any point in doing all this, because angular momentum from a perspective and sweeping and gravity, that's a whole different kind of angular momentum than just considering the simple truth that angular momentum is just regular momentum. It's just a mass moving a velocity, and it can be calculated as a particle in a location moving a velocity. So there's absolutely no need to make it complicated.
And then you look not exactly down at the 8, but at a slight angle, it should look like a little bit less than 8. Now, 7 is not a little bit less than 8, it's a definite amount less than 8.
So now he's just talking about relativity, and you can't change how much it is. It is in a reality, and how you're looking at it doesn't change the reality. So that's all just nonsense.
So the darn thing can't...
You can't make things bigger and smaller based on changing your perspective. Your perspective is irrelevant to what it is.
Physics, of the various principles, there are deep interconnections between the things, so that one implies the other in some way. For example, the relation between relativity and the necessity for local conservation, which if I said that without the demonstration...
So forget this local talk. It's just more mush.
Why the rockets in empty space can't go. But they do go. That's because we have an area at a certain rate. After the mass has moved over here, if it's going up at the same speed because the box is drifting, then the area would be increasing at a greater rate because there's a bigger length this way, although the altitudes are the same.
So he's really talking about the angular momentum in the center of mass, and it just, obviously, it just, it's just momentum. Obviously, center of mass is important to understand how an object will move.
But by the conservation of angular momentum, you can't change the rate at which the area is changing, and therefore you simply can't move one mass from one place to the other if you don't push on something else and get rid of the momentum or angular momentum. And that's the reason why the rockets in empty space can't go. But they do go. That's because we have, the rocket is what the center of gravity, that is, if you figured it out with a lot of masses, if you move one forward, you got to move the others back so that the total motion back and forth of all the masses is nothing. Now,
so that's not really what happens. What the rocket's doing is giving away stuff that contain momentum in a direction, and now it has an imbalance in the other direction. So it's just back to you. If you have two forces hitting you, 5 this way and 5 this way, and you give away the 5 that way, well, then you're stuck with the 5 this way.
The way a rocket works is that is a rocket.
So we know it doesn't work for kinetic energy. So that's what I wish he would have done, is say, well, if we calculate the kinetic energy of the exhaust, it won't equal the energy the rocket leaves with. And if I want to get the equal and opposite reaction of Newton's third law, I have to calculate the momentum of the fuel.
Shoot some gas out of the back, and here's a gas. You see, beforehand, the rocket's standing still, say, in empty space, and afterwards it shoots some stuff out the back, and then the rocket's going forward. And the point is that of all of the stuff in the world, the center of mass, the average of all the mass, is still right where it was before.
Right, but that only works for momentum, because if you calculate the kinetic energy, you have a lot more kinetic energy going that way than you have going the other way.
But the interesting part is moved out here, and an uninteresting part that we don't care about is moved out here. There is no theorem that says that the interesting things in the world are conserved, only the total of everything. Discovering the laws of physics is like trying to put the pieces together of a jigsaw puzzle. And we have all these different pieces, and today they're proliferating rapidly. And they're lying about. Many of them can't be fitted with other ones. Now, how do we know that they belong together? How do we...
Okay, you do it by doing experiments, and they haven't done any. So again, they haven't dropped 4 pounds 1 foot and 1 pound 4 feet. They haven't done anything to tease the truth out of the physical world.
We know that they really are parts of one picture, one at present incomplete picture. We're not sure, and it worries us to some extent, but we get encouragement from the common characteristics of several pieces. They all show blue sky, or they're all made out of the same kind of wood. Thank you very much.
Not much of an ending. Anyway, so yeah, they all have the speed of light. Yeah, maybe it's all the same force. Maybe gravity can't be bent space because, frankly, it's moving the same speed as all the other forces that aren't bent space. That aren't bent. All right, so enough of a video and such. Plenty. So, till the next time and such and so forth and whatnot. I ought to quit playing with this thing. Anyway, so till the next time. Blah, 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 blah.